in the sort of traditional sense, which is known as Kaluza-Klein theory. So there's sort of two ways in which we actually work with gravity in a contemporary sense. Either you're doing gravity in the context of astrophysics, cosmology, you're describing the universe, you're talking about black holes or gravitational waves, in which case you don't even think about dimensionality, you're obviously in 3+1 dimensions, or else you're thinking about gravity as it fits into high-energy physics as some sort of more fundamental theory, in which case you tend to sort of often flit around between dimensions a bit like a butterfly. So, dimensions are something that's sort of not fixed. There's no sort of definite sense of numbers of dimensions, and actually quite often you're projecting down holographically in terms of, from one dimension less. And it turns out 4 is an interesting number of dimensions for gravity, because it's the lowest dimension in which gravity freely propagates. So you can think of this either as gravitational waves. There are no gravitational waves in 3 dimensions. But it's the lowest dimension in which a space-time can be Ricci flat, but not Riemann flat. So you get, which are tidal forces, essentially. So in 3 dimensions, you still have gravity, but it's quite trivial. You only get space-time curvature where you have energy momentum. So it's all, all localized where you've got matter. But in 4 dimensions, we have tidal forces, which is like the free squeezing or deforming of space. If you go up from 4 dimensions, you then find, again, the geometry side of things is very similar, but not the physics. So in 4 dimensions, we've got our centrifugal repulsion looking like 1r squared, and our gravitational attraction looking like 1r squared. And so you can have the two balancing out and have orbits. But it's sort of fun in 5 or higher dimensions. Your gravitational attraction now goes like 1/r cubed, 1/r to the 4th, or whatever. And so you no longer get this balance, and you don't have solar systems, for example. Also, your shoelaces would come undone in higher dimensions. So there's all sorts of interesting things about the way dimensionality changes the sort of things that we're very used to. That sort of changes aspects of our universe around us. So, why would we want extra dimensions? Well, from a formal perspective, why not? Why should we be in 4 dimensions? That's something we can explore. But also, I think that the primary reason these days that we think about extra dimensions is the steer that comes from string theory. So, the string theorists sort of tell us, well, you're basically either in 10 or 11 dimensions at a fundamental level. So what happens to those extra dimensions? So we have to be able to explain why we only see 4 dimensions, why our effective theory is 4-dimensional. And so there are essentially 2 ways of doing this, and Kaluza-Klein theory is the first way, which is that you hide your extra dimensions by making them very small. So that's the sort of sweep it under the carpet technique. So the notion here, and the reason why this is the sort of standard way, is that Kaluza and then Klein were looking at the early days of gravity at what would happen if you had an extra dimension. So their thought was that the symmetry, if you didn't have anything depend on the extra dimension, the symmetry in the extra dimension would have a parallel in the gauge group of electromagnetism. So electromagnetism has a U1 gauge group, or R. And so it's got this translational symmetry in the extra dimension. And so they noticed that if you, which we will be at least outlining, that if you took the gravitational action in 5 dimensions, it sort of looked like Einstein-Maxwell, sort of, in 4 dimensions. And so, I don't think they thought of this in any real sense, but it was nonetheless something that was very interesting. The 2 massless interactions that were known of, that gravity and electromagnetism could kind of be unified. And it took Einstein quite a long time to kind of believe this and accept it. But now this is our sort of standard or canonical way of hiding extra dimensions, and there doesn't just have to be one. So, Kaluza-Klein theory. So you can think of it as taking a gravitational solution and kind of just adding translational degrees of freedom. So that's really what Kaluza-Klein theory does. And so you have something that looks like this. So the extra dimension here is curled up on a size or a scale of L. So mostly it was assumed for many years that that scale would be the Planck scale. But it doesn't have to be, and it gets more interesting actually if it isn't. So what does this do for us? Well, if we think about it from what might, gravity isn't the only thing that we see. We've also got field theory. So what happens to the wave functions if we've got this extra degree of freedom? So saying that something doesn't depend on extra dimensions sounds very restrictive. So what would happen if things did depend on extra dimensions? Well, you'd kind of have to have a factor that, say, looks like e to the I chi, if our chi has periodicity 2 pi. So that's now a single-valued wave function. But then if we look at our sort of 5-dimensional wave operator acting on psi, and peel off the bit that depends on 4 dimensions, this looks like the equation of motion for a massive particle. So this would be our m squared. And because L is thought to be small, we don't see it, that mass is very, very big. So there's this notion, therefore, that things could depend on the extra dimension, but they would be have very high masses. So if the extra dimension were something like the Planck scale, you'd be talking about Planck mass excitations, and that's way beyond any energy scale that we're interested in. So what we're interested in is something that just happens at low energies, and therefore we don't have anything dependent on chi.
Is the exponential normalized by, is it chi over L?
Well, no, because I've said chi has periodicity 2 pi. So now everything, if you're going to have, you could even have in chi, in which case you'd have n squared on L squared. But you get this tower of massive modes, but the idea is if L is very small, these modes would have incredibly high mass. Now, this is not what Kaluza and Klein were thinking when they did it, but from our perspective, why would we be interested in this century-old idea? why is it relevant? Well, it can describe low energy physics below the energy scale of the sort of set by the size of the internal manifold. So now let's think about gravity. That's sort of saying why we might expect our relevant low energy physics just to be independent of this extra direction. And I'm going to split up I'm going to write the metric in this very general form. So this is just, everything here just depends on x. So this is sigma of x mu, this is a mu of x. So my gzz, or the extra, is the size of that internal direction. Gzx, there's 4 of those. And then this is what's left, so g mu nu. So I've just split up my metric in a very specific way. And the reason I've done this is so that root of g5 is e to the sigma root g hat 4. There's also another reason for splitting it up that way, is that it sort of sets the scene for computing the curvature. So here we've sort of split things up into g hat, which is like a tensor, a, which looks like a vector, and sigma, which is a scalar. So with respect to our 4-dimensional space-time, the 5-dimensional metric decomposes into 3 sort of natural degrees of freedom, a tensor, a vector, and a scalar. So the handout that David's printed for you has all the details of the calculation of the curvature. I just want to pick out, I guess, a couple of key steps that are, I think, relevant in the calculation, and also kind of pick up on some questions that I've had. So if we use the Cartan method, here this is an example of a metric with off-diagonal terms, which I've been asked about. So when we sort of start thinking about that way of completing the square in the metric, it gives us a very natural gauge potential, A. So we can sort of see how we're going to get Maxwell theory coming out of this. But in terms of finding our connection, you kind of saw this when we did the domain wall, or this type of thing. It's when we do our differentiation, the differentiation of these basis of one forms is usually very straightforward. And what we're left with here is actually a set of simultaneous equations. We found d omega, we want this theta. So these are just algebraic relations. And so when we unravel them, it's sort of fairly obvious that the connection 1 forms with mixed 5 space-time coordinates, indices, obviously has one that looks like d sigma, but then you've got this second term, this f lies purely within 4-dimensional space, the sort of 4-dimensional subspace of the space of 2 forms. And so, yes, we identify this, but now when we go back to try and unravel what theta AB is from this relation, we've got to that d omega A is not just theta AB cross omega B, but there's also a theta A5 cross omega 5. So this is going to be non-zero now. And so we also get an F term in theta AB. So that's just kind of trying to draw attention to one of the steps of this calculation that's just a little different from the things we've seen before. Most often when we're looking at exact solutions in GR, they quite often are block diagonal in terms of metrics. So, we get a long way without needing an off-diagonal metric. However, when we do find one, this is how we deal with it. We just don't get too, don't be too sort of quick about reading off the connection components. Remember, it's a series of simultaneous equations, and so you're just solving them. It's still straightforward. You just have to remember what it is that you're doing. The computation of Riemann is now straightforward. And that's on the handout. Don't want to be putting hats on everything, so. So I've just pulled out the ones that are relevant. Again, the details in the handout. But if we're interested in either solutions to Einstein equations or the Einstein action, all we need are components of the Riemann tensor that contribute to that. So there are more non-zero components, but these are the ones we're interested in. And so what you kind of notice from a pattern perspective, so a lot of sort of doing calculations is actually about becoming experienced with spotting patterns. You see here that we've got, rather like the Gauss-Codazzi breakdown of the Riemann tensor, we've got a sort of background Riemann piece, and then we've got an FF term. So this is kind of like, it's reminiscent of the KK, the extrinsic curvature terms in the Gauss the Gauss equation. So these are the sort of relevant parts that we need. And then if we compute our 5-dimensional Ricci curvature, we find that it's given in terms of our 4-dimensional curvature. I suppose rather than 0, I should put that as 4. F squared, so that's like the Maxwell piece. And then we have a piece that I've kind of recast in terms of what will end up being a total derivative. So we put down what the square root of G5 was. So together, our Einstein action So this is what I get when I put together all of the ingredients for my Einstein action. So the integral with respect to z can be done because that's nothing's dependent on z. And this integral here is just going to give me essentially a length scale. Then whatever the periodicity of z is. Then if I look at the rest, I would say, okay, this last piece here is a total derivative, so I might be a bit confused by that last piece because it sort of seems to be saying that there's no kinetic terms for the scalar. So that's just what's going on there. But then, if I look a bit further, I've also got this term here and this term here. So kind of picking apart my action, I'm seeing that, yes, it does look like Einstein gravity, but there are a few key differences. And probably the most important thing is that scalar field. I can't just throw it away because it's pre-multiplying the Ricci scalar. It's also hiding with the Maxwell piece. So the Ricci scalar, we saw when we did the variation of the Einstein action that we had Palatini's lemma where we wrote our delta RAB in terms of covariant derivatives of differences of the connection. And in the case of the Einstein action, that just gave us a total derivative that gave us the boundary term. However, at the time, I sort of remarked, well, if there's anything else pre-multiplying the Ricci scalar, when you do that integration by parts, you're going to get derivatives of the scalar coming into your equations of motion. So yes, there are no manifest kinetic terms for the scalar, but when you do your variational principle to find the Einstein equations, or what are the new Einstein equations, you will find that derivatives of sigma come up naturally as part of that integration by parts. So it is misleading to say just because there's no explicit kinetic terms for the scalar that the scalar doesn't have equations of motion. So we call this scalar tensor gravity. So it's a gravitational action, but the nature of the gravitational interaction isn't just spin 2. It's got a scalar field in it as well. And of course, we've got the scalar terms multiplying our Maxwell piece of the action as well. So this sort of appearance of a scalar multiplying the Ricci, we call this G hat AB. We call this the Jordan frame. So it's a choice of metric in which our gravitational action has scalar multipliers. So the sort of late 50s, early 60s, people were interested in investigating scalar tensor gravity because of essentially Mach's principle, which was something Einstein had always kind of been a bit preoccupied by. It's this notion that when we just take the Einstein action, we are left wondering, say, if we spin a bucket of water in space, an idealized bucket of water, the water will be pushed up to the edges of the bucket because the thing is rotating. So how do we know we're in a rotating frame? So that's essentially this question. How do we know we're in a rotating frame? How do we know we've got a gravitational attraction, sort of with respect to what? And so the notion was, well, you know you're rotating because you're rotating with respect to the distant stars, or if you like, with respect to the rest frame of the universe. But then that sort of begs the question of how do you define a rest frame? And so then the philosophy was, well, it's the whole matter content of the universe that's kind of defining this rest frame or defining things for us. And so you kind of got to this idea of, well, maybe the gravitational constant, which is telling you about sort of gravitational inertia, maybe that's something to do with the rest of the mass in the universe. And so here, when you work through your equations of motion, you kind of find that this scalar responds to the trace of energy momentum. And so the scalar sort of changes when you've got matter in the universe. But what is the scalar? Well, if you think about it, it's something that's pre-multiplying R. So what pre-multiplies R in the Einstein action? It's 1 over 16 pi g5. So it's 4. It's the Newton constant. So changing the scalar is changing the strength of the gravitational interaction locally. So that was kind of where people came from and why they thought about, well, how do we describe this process? So why is it called a frame? Why is it the Jordan frame? Well, one thing that we can do is a conformal transformation. So a conformal transformation, as you know, is something which changes lengths but not angles. And what that means is it's a scalar transformation on the metric, changes, it sort of rescales lengths, but it's not rescaling angles, because angles, you know, if you remember sort of the dot product formula, the dot product, the cos between two vectors is A dot B over mod A mod B. So if you rescale what A dot B means by just a common factor, it doesn't change the angle. So this is the sort of general statement of that. And if we do this, then our Ricci scalar is rescaled as well, but we also get derivatives of the conformal factor coming in. So if we choose a particular value for our conformal factor, which is related to this scalar field, so first of all, if I just write out what root g hat r hat is, here is the r hat, and here is the root g hat. When we take the determinant, we get a factor of omega for every single dimension of g hat, so that's omega to the fourth. Then I input, for this choice of omega, so now I've shifted to root GR. So this part is the standard Einstein action. We've got a total derivative, this piece, and then out here we've now got a kinetic term for our scalar. So doing a conformal transformation shouldn't really change our degrees of freedom. If we got gradient terms in our equations of motion through integration by parts on the Jordan frame, we should still be getting gradients on this new frame, which we call the Einstein frame. So we obviously have to get some kinetic terms. So the final step to getting our Kaluza-Klein action is to redefine our scalar. So we write phi as sigma over root 3. And so that's what we get. We've kind of rewritten our metric in a rather specific way, but by doing so, we now have something that looks extremely familiar. We've got an Einstein action, we've got a kinetic term for our scalar, and the only way in which we see things being a little bit dodgy, if you like, is the fact that we've got this scalar term multiplying the Maxwell term. So that is our sort of specific dimensional reduction with one extra dimension. Of course, you can have more extra dimensions, in which case, if you have more extra dimensions, you've obviously got, you have this sort of same notion here of dz plus a gauge field, but now this z here was, if you like, in the case of one extra dimension, was a killing vector of the higher dimensional metric. And so if you have a killing group now, like let's say you had a sphere as your internal manifold, you would then have 3 killing vectors, and so for each of those killing vectors, you'd have a potential gauge field. So that's the only thing that changes. If you have a sort of more symmetry of your internal manifold, you then get non-abelian gauge, sort of 4-dimensional gauge theory. So let's sort of stick now with this straightforward example of one extra dimension, and let's ask what happens to black hole solutions. So here I'm kind of relying on the fact you've met the Reissner-Nordstrom solution either in tutorials or the previous course. Yep. So what we'll see is that Kaluza-Klein black holes look a little bit like Reissner-Nordstrom black holes, but with important differences. So the first thing I have to note is that compactification actually means that this A mu term is important. So remember when we did the domain wall, I said that I wrote it down as, I suppose if I go back to the top, I wrote the metric down as the 4-dimensional metric, but with one extra direction being the proper distance from the wall. So I could do that then because I was making no assumptions about the range, if you like, of that proper distance. Whereas here, we're saying our orthogonal distance is identified at a very short range. And what this means is that we actually pick out a rest frame. In other words, we can't just gauge away that A mu. So it's perhaps easiest to see by just sketching. If I have T and Z, here's my null ray, and I look at T primed and Z primed. So that would just be a Lorentz boost. I now represent my finite extra dimension by a line. So Z is identified with Z plus L at constant T, and that's the key thing. So if I do a Lorentz transformation, this is my Lorentz transformation for T primed and Z primed. Then Z being identified with Z plus L becomes Z prime is identified with Z prime plus gamma L, but also T prime must also be simultaneously re-identified. So we are identifying points at different times. So we're identifying here, if we'd already compactified in the TZ direction, when we actually had a Lorentz boost, we'd then be saying we were now identifying points at different times, at different T primes. So what does this do to our black hole solutions? Well, the first thing is, let's start by getting a black hole solution, or rather a black brane solution, because we started off by saying our geometry couldn't depend on the extra dimension. So I can't have a black hole in the 5 dimensions. It's got to be translationally invariant in the Z direction. And so fortunately, it turns out that our very simplest solution, the Schwarzschild solution, if we translate it in the extra dimensions, so we just get a black string, that's also a solution of 5-dimensional gravity. I scared them off. So this is a solution to 5-dimensional gravity, and it just looks a bit like it's a black string. So that would be just our simplest Kaluza-Klein black hole solution. Uncharged, translation invariant, nothing happening in the Z direction at all. So if we now think, well, let's do a boost on that and then identify, what would we have? So if we boost before identifying, all I do is kind of replace a sort of Lorentz or inverse Lorentz expression in, replace t dt with gamma dt plus v dz, and replace dz with gamma dz plus v dt. And at this point, I now compactify by saying, let's say z becomes psi, which is identified with, well, actually, let me just say z is identified with z plus L. And then I sort of multiply out these brackets and then rearrange to get things in the form that we've got on the top blackboard over there. Phew. Right. So the first thing you notice is if you do this Lorentz boost, you're kind of introducing cross terms in the metric between t and z. So when you rearrange things and sort of complete the square for the dz part of the metric, you know that your gauge field, a mu dx mu, is just going to have a t component. So what this is saying is that a boost in the z direction has given you an effective electric charge. So this shows that you can identify velocities in the extra direction with an electric charge, you know, in the sense that this is this Kaluza-Klein electric charge. So So this metric's still a bit of a mouthful, so we can think about trying to make it look a little more familiar. We notice that the GTT, or GTT hat to be more precise, is kind of like the Schwarzschild form. It's still 2gm over r, sort of, except our mass seems to have been rescaled, and also we've shifted the origin, if you like, of the r. It might be more natural to redefine our radial coordinates such that this looks like 1 over r. Mm-hmm.
Sorry, could you explain again what you mean by identifying the velocity with a charge?
Well, because we've done a boost before we've identified. So a Lorentz boost is just what happens when we're moving in a moving frame, right?
I guess it's the charge I'm confused with.
Well, so you take the cylinder, that was what you started off with, the black string, and then what you're doing is you're saying, right, now I'm boosting this. I'm giving it a velocity before I do this identification. So you're boosting it in the z direction, and that's this transformation here, this Lorentz transformation. And having done that boost, that velocity, now you insist that you do your compactification. Z goes to z plus L is a you know, that's the sort of finite range of that z coordinate. So you've, if you like, got one of these black strings. A periodic coordinate becomes like a black donut or torus, but it's, you know, just because you've got a finite extra dimension. But it's saying that if you have the black string with no velocity or a black string that's going in this extra direction, these are two distinct solutions. So that the velocity in the extra direction is showing up here as an electric charge from our four-dimensional perspective, because we've got an AT coming from that Lorentz transformation. So that's what it means. It's just saying that by boosting in the extra dimension, what you're getting is something that looks like electric charge, in the sense that here you've got a potential. So all I'm doing here is just redefining coordinates and charges and things just to make things look a bit more familiar. And then what we get for our Einstein frame metric So what I get from my Einstein frame metric is this This is our final Kaluza-Klein electric black hole. So what you see, what's the effect of what I've done? Well, this first bit, the effect of just rewriting coordinates has been to make the Schwarzschild potential look normal. But the reason we've got this extra piece here is because in our transformation between the Jordan frame and the Einstein frame, we've got some factor of the scalar field. So we kind of got the square root of this. And that's 1. I'm wondering if I've got a sign there. 1 minus VQ on R. I have a feeling that might be a minus sign, but we don't worry about signs usually in real time. And so by doing this conformal transformation, you kind of pick up all these different extra factors. So this is what our Kaluza-Klein electric black hole looks like. And notice GTT and GRR are still inversely related, but now R hat is no longer this areal radius. Just like Reissner-Nordstrom, you can have an extremal limit of the black hole, but the extremal limit here, which is kind of where Q goes to M, then this is now singular. So there are differences in terms of how the black hole, or what, the properties of the black hole. But what I wanted to finish off talking about, because it's kind of cool, is the magnetic black hole. So for a magnetic black hole, what you do is you take the field strength and you make it proportional to the area form on the spheres surrounding your object. So in this case, that's a 2-sphere. So if I have this, dF is 0, because the only functional dependence you've got in that is theta. So, but we cannot write F is d omega except locally. So this is an example of a form that is closed. In other words, d of the form is 0, but not exact. Exact means that you can write the form as d of something. So when you have closed forms that are not exact, it's usually a sign of something happening with the topology of your space. In this case, our topology is non-trivial. We've got sort of non-trivial closed 2 spheres, because we've got the event horizon. If we try and shrink our 2 spheres, we hit the event horizon. So we can, of course, write F as d omega locally. I suppose I use locally in a general sense. So I can write my magnetic solution as dA, and call it north. The N and S stand for north and south. I have a gauge patch which works round the North Pole, everywhere but the South Pole axis, and AS works everywhere but the North Pole axis. And between the two are related by gauge transformation. So if I make this ansatz for A, in other words, I look for a solution of 5-dimensional gravity where my A mu up there is equal to this, one of these A's, A north or A south. Okay, so that's what you get for the solution. So you're looking for a general solution. I haven't said what M is, but obviously M is kind of related to R plus. Like the Reissner-Nordstrom solution, and like the electric solution, you have two horizons, an outer and an inner one. The first horizon is sort of more to do with the black hole. The second horizon crops up because of the charge. So here, where I wrote it down, I've kind of written things in so that this here is the North Pole A. So I could have a South Pole patch But now something interesting happens. If I go round in the phi direction, round the circle, I go to phi plus 2 pi. And so this tells me that I've got, because this is my z direction, I have to make sure that I get back that this 4 pi q corresponds to the periodicity with which I identify z. So either 4 pi q is L or 2L or 3L or whatever, but I have to make sure that these 2 points are the same points. So this, if you like, has to be identified with z south plus L times n for some integer. So what this means is that charge is quantized. So in fact, this was something that Dirac noticed back in the 1930s, and he was very interested in the fact that should there exist even a single magnetic monopole in the universe, that would be responsible for the quantization of electric charge. So here, it's a little bit, this sort of link with electric charge comes through the, actually through this L. This L is telling us about electric charge in Kaluza-Klein theory, but it's actually the same sort of argument that Dirac used. In Dirac's case, he was looking at wave functions of electrons and thinking about, that they had to be single-valued. Here, we're looking at the geometry and saying that if we have a periodicity of our z direction, and that is mixing with the phi angle, these two periodicities have to be in alignment. It's the same, actually the same argument, but sort of different a different physical manifestation. One charge is a charge of a wave function, the other charge is a charge of a geometry. So, but it's the same reason. So now let's look at the extremal limit, which is really what I wanted to talk about, because there's some nice little bit of maths here. So in the extremal limit, Q is R plus, and I'm going to say that that is L over 4 pi. So I'm saying that Q is the smallest it can be here. So I'm going to let chi equal 4 pi Z over L. So the periodicity of chi is now 4 pi. So what we see is that if r plus is r minus, our time coordinate now completely becomes just an extra coordinate tacked on to the geometry, and we have some non-trivial spatial manifold that kind of just exists in time. So let's look at what happens when r goes to q. We kind of saw this when we looked at the Euclidean Schwarzschild metric. So it should be no surprise when I try and take the square root of r. So now what happens is there's a common factor sitting in front of the d omega squared and the d chi squared part. But something interesting's happened, because just like in Schwarzschild at the event horizon, when we take the square root of the radial coordinate there, and we find that it looks locally like the origin of r squared, actually here, this thing here, this part, is the origin of R4, where we've done a slightly different parametrization of the three sphere surrounding the origin. We've used Euler angles to describe the three sphere. So just to... So you've got the transformation that you can check it works. So what we've got here is a way of mapping locally to the origin of R4, and if we sort of look at what we're doing, is we're fibering S2 by S1. So when we take a Kaluza-Klein compactification, we're always adding a little manifold. Here it's a little circle, but we're fibering the S2 with a twist. So if you like, around the equator, imagine sewing on bits of chainmail to a sphere, and you do it on each half of the sphere. But then to stitch the two halves together, instead of just doing a simple stitching of, of sort of ring to ring, you start off by stitching a ring to ring, then you move one step along, but as you move a little delta phi around the equator, you also twist the chainmail by delta phi and then stitch together. So by the time you've gone all the way round, you're back to where you started, but you've done this full 2 pi twist. And what this does is it lifts, if you like, the S2, 2, and S3. So it's not S2 cross S1, it becomes an S3. And this is an example of a Hopf fibration. So S3 is kind of an interesting manifold. It's a group manifold. We've got the fact that we can coordinatize it with Euler angles. Euler angles are angles that we parameterize SO3 by. So the coordinates of our manifold also define for us the elements of the group of SO3. And of course, the symmetry of S3 is SO4, which actually has 2 copies of SO3 in it. So the symmetries of S3 or SU2 cross SU2, either way. Whichever way, locally anyway, the algebra is the same. And so you actually see this as the transformations acting on left and right. So we have both a left action and a right action of SO3. And this gives us 2 SO3 killing algebras. And what's happened for our geometry here, if we look at it, we know we've got an SO3 algebra because we've got the d theta squared plus sine squared theta d phi squared sitting in there. We've also got a U1 because of the d chi, but we don't have the full SO4 algebra. And what's happened is we've kind of broken the symmetry of one of these SO3s that act on the S3. And what we're left with is the symmetry of our metric is SO3 cross U1. So it's kind of one of these examples of sort of we've got these 4-dimensional, this is a 4-dimensional Euclidean metric, where we start off with the S3, and then in this case we've squashed it. We break the symmetry in specific ways. But I know there's another lecture, so I'm going to stop.